A warm welcome and very good morning and signing Sunday for everyone, all of you. It's my pleasure and privilege to invite you all for this invited talk. And this topic is an amazing topic and speaker is an extraordinary speaker. So the topic you can understand, recent trends in protection and aiming for the future grids. That's the topic. So let's probably not waste our time. We have very short time. So let me straight away jump into this means what say introduction and like I will keep my time as short as possible. Right? We are going to talk about this recent trends in protection of future grids. And this is an invited talk, and we thought of inviting quite a lot of experts from outside to probably enrich the world. And today's eminent speaker is Sethuraman Ganeshan sir. He is an advisor in energy sector. Sethuraman Ganeshan is an electrical engineer. It means he has completed his electrical and electronics engineering degree from College of Engineering India. If I am right, it is 1982 from Chennai, and the 150-year-old college now. And he has started his career immediately after his BE in TCE, an eminent power system consulting engineer in India. Of course, the power plant consultants, and like if you take means was it some 20-30 years back, this is the company which probably dominated the complete consulting business. Then he has moved to the GE, that is English Electric by then, right? And then to ABB. Like ABB, he has worked in almost all the countries, right? Turkey, USA, India, and probably means what say he has worked in almost all the sectors. He has worked in almost all the sectors, and that's systems, government services, and R&D. His technical expertise includes facts, microgrids, assessment, renewable storage, electric vehicle infrastructure. He was also like a chair of Power and Energy Society, that is PS IEEE Bangalore chapter. In 2019, means what is the chapter has honored him with an outstanding engineer award, and he holds a few patents and has a number of papers to his credit. And presently, he's not few, that's his words, like he's advising quite a lot of energy sector firms in today's.
So good morning, everyone. Let's quickly jump into what we want to discuss here today. So I always say one thing: when you want to do a protection of a system, it's like you are like a doctor and you need to know the human being anatomy very well. So also a protection engineer can be a good protection engineer unless he understands the power system very well. So that is the fundamental thing which I would always suggest and insist. So of course, I saw one note recently from Sabha saying that people just do either paperwork or they do only using a software. So either extreme is not good. You need to know what you are doing. You should have the insight and you should be able to apply computer to the fullest advantage. So naturally, you need to know the analytics of power system with respect to fault or load condition. And so as to make sure, this will make sure that the protection would take out the minimum portion of the faulted system out. It should not take out healthy system, and it should definitely take out the faulted system. So in this discussion, we are discussing more about the power system rather than the individual, the safety and other aspects of protection here. So you might have seen the picture on the right where it shows the whole globe nicely illuminated. Of course, I just wanted to always highlight this is not a realistic picture because at any one point of time, the Earth is illuminated 50% of the area by the sun. So this is very important. Remember this point. We will talk about it a little later. All right. So today we talk about the art and science of protection, but more on art than science. We have two parts of the left. One is, on the brain. One is left side and the right side. I don't say left side is wrong side. Left side is one of the sides here. That's a joke we normally make. So right side is about your imagination, intuition, and all that art definitely is perceived on the right side or conceived on the right side. So we'll talk a little bit more. So we'll possibly let loose our imagination and discuss about the future, some of the latest approaches, technologies, and research areas. We will not dwell too much upon the classic protection methodologies and some of the challenges you may have, some of the system issues you may have. That is not the main focus. You can always take it up offline, or you may post a question so Lokumar and team or I can possibly answer them later. So the purpose behind this is that within the limited time we have, we wanted to cover as much interesting topics as possible. Some of you are possibly very young and possibly straight from college or in the college. So you may want to know a few things about how things are evolving. Many of you might know it already, but it's a good thing to recapitulate a few things here. That's the idea behind the whole presentation here. Okay, so I'm just trying to quickly give a highlight of what we are going to do today. We will first talk about the grid and protections as they exist today. I'm as again going to talk about some of the latest ones and how future grids are evolving. Then we'll also talk about how we could possibly think of protecting the evolving grid and the future grid, how and where it is heading, and some discussions at the end. This is in short what we'll see today. Now, this is something very fundamental. I think as protection engineers, we all know there are fundamentally few aspects, or I would say some of the aspects you would definitely look at. You want to have a very high speed protection. At the same time, you want to be sensitive. It should be accurate, dependable, secure. I'm not going to get into definition of all these important parameters, but this is what it is all about. And the result that you maintain a power system. And I always take pride that I am one of the protection engineers who is balancing all this the power system work. And if you know, or if you remember rather, the power system is one of the biggest machines on earth, right? It is spanning across multiple continents sometimes, and eventually we'll talk about grid across the globe. Why we should do it is also something very interesting for us to know. Anyway, this is something very classic sequence in which protections have evolved. I started my career long back when the electromechanical relays very much in vogue. Static relays were coming, and then the digital relays here I would use because I am very familiar with some of the relay development. We used to use microprocessor basically for doing logic functions, not for measurement aspects of it. So measurements were done by conventional static components and decision making and some of the timing functions, tripping logics were all executed microprocessor. That's what I would classify as digital. And latest and not the least is the numerical protection, wherein we do the analog to digital conversion upfront inside the relay and then do further processing. So that's all we categorize under numerical processing. Now, where we are heading from here, that's what I think most of you would like to know. I think this is what I expected actually 10 years back, and nothing like that has really happened. I imagine that in future, the IED as we know of it today may possibly shrink, in both in size as well as in functionalities. More and more things may be done in possibly redundant computer systems locally for very critical time critical functions, and some of them may be done in the cloud. So this is what it is all about. So I don't want to go beyond the 80s. We all know that. So after 90s, we talk about some of the protections like transient and traveling wave, wide area protection, cloud. All these things are all terms which we typically try to use as we evolve into the future grade and future protections. So we all know this term IED, right? Intelligent electronic device. And if you look into the way we build IED, because I've been part of multiple organizations wherein we build these IEDs, it is just another module, or you can say earlier we used to use the term programming, but it is some app today, right? So technically you can have the same hardware roughly, and you can have distance protection or differential protection or whatever protection you want. You could possibly populate that particular hardware with these protection modules. So today, if you just walk across to any customer or any of the young people, they'll say, no, I have IEDs, they do this, that, and everything. But remember one thing, the fundamental thing it should do is protection or relaying, right? So all the other things are all built above that. So that is the basic core, the soul of your IED is the protection. That's what I would always try to insist, because some of the newer generation people, they may not understand that one line or one bit of wrong information in the coding can cause havoc. It does cost. I don't want to get into the details. So this is very, very critical. So protection, you should give utmost care when you design, build the latest IEDs or software for that matter. Now, this is something I just wanted to give for making the situation a bit lighter. I'm sorry if it is not exactly in line with what you were expecting in this talk. As I said, it's more about imagination and other things than pure technical stuff. This is maybe 5-6 years old when possibly iPhone 6 was there. People who have these very expensive iPhones and they fall down, they are not worried about their leg or their body, but they are more worried about the product they are buying. So also today, I find the general tendency in the industry is to worry about what the IED does, everything. But again, remember, it has to do protection. That's the reason why I have put this picture here. And moving forward, I think most of you might be aware that this is a representation of a typical high voltage switchgear, maybe 66 kV and above, all the way up to 800 kV or 1200 kV we are talking about in these days. So we have isolators, breakers, current transformers, voltage transformers, protection, controller, and multiple merging unit. And today, some of the current transformers and voltage transformers are all conventional. And moving forward, we may have more of the latest technologies, including optic current transformers or voltage transformers. By the end of the next decade, I think we will not have any of these IEDs as we know today. So they are all going to be doing basically software functionalities. Everything will come from digital fashion from the power system as such. So the IEDs today, where we make it suitable for transients and other things, may not exist so much, So it's going to be a slightly different picture. So this is what we call as digital substation in short. So this is on the substation side. On the switchgear side, it has already happened. Most of the current transformers and voltage transformers are of the latest technology with digital outputs directly connected to the IEDs. And you don't find any more conventional switchgears, lamps, annunciators on the front. We have possibly a single IED which is on the front, and that's what you use it for interfacing with human. Now, where is the protection going? We all along, all this almost a century, I would say, protections have been reactive. They sense currents, voltages, frequencies, or whatever you may name. They continuously monitor them, and if things go wrong, then they do some action. But moving forward, we are possibly getting into an age when we are able to process this information thanks to a highway, typically a digital highway to the last equipment in the switchyard, right to the isolator, I would say. We have so much of information available to you in hand that you are able to do very big data analytics. And so you are able to say where the particular equipment is heading with respect to its reliability. Typically, we all know that a transformer, you would do possibly a dissolved gas analysis, maybe once in a year or once in a few months. You may tap something and then take the data manually. You would analyze, oh yeah, okay, this level is lower than what is expected, and I can possibly do something about it. So that's a typical thing. But today, thanks to more and more digitalization, we are getting more information online. We are talking about the online DGA, and we are talking about the protection modules inside the IEDs. They also have additional modules to monitor, let's say, the thermal content of a transformer or motor or cables or whatever you may name. So we are able to get all this data, and we are able to get actionable items derived from this data. What is going to happen eventually? I'm looking forward for the day that the protections may never ever have to operate, right? So you do so much of prediction of the life of the equipment, and you are able to do it so much. Let us say, I don't say we are going to completely eliminate protection tripping, what do you, in a catastrophic way, but we may be able to reduce uncalled for, unknown tripping in the system so much. And even on the line protection aspect, that's a different ball game. I'm not talking about that at this moment, but eventually we may get there also. But idea is that today the protection is heading more or less towards that direction. That's all I wanted to highlight. And to that extent, we always fall back on some of our experience in the past. I typically recall in the early 90s, company like GE, in collaboration with Texas A&M, they pioneered some of the artificial intelligence data analytics for the medium voltage distribution lines, say typically 13.8 kV, 11 kV, or 22 kV lines. When they fall down, you are not able to detect them, and people may go and touch it, and then or they may go close to it and may get electrocuted. So human safety is one aspect of it, but all the same, as protection engineers, we are never able to know that there was a fallen conductor, because we are looking at very high current levels which are not consistent with the currents you would normally draw when a conductor falls on some vegetation. So today, I think this technology has been adapted in most of the other manufacturers also, including ABB and Schweitzer and other companies. But what I'm trying to say is not about the availability, but generally how protection has evolved from a simple overcurrent at fault distance protection into more and more data analytics and processing. And that path we are continuing further for detecting things in advance and trying to protect the equipment and eventually the power system as a whole. So this is just a small pictorial representation of what we do for a typical transformer, collecting the gas and trying to analyze it. So moving on, how the grids are evolving. But before that, just to let us take stock of what has been happening in the last few decades. We know, as power system engineers, that for decades, grids have been dependent on underlying physics operating principles, right? And of course, the measurements like inertia, frequency, voltage, and we all know that frequency is an important measure which indicated the well-being or otherwise of the grid. Let's say we have an overload in the system, the frequency will slightly dip down. So you know that you need to possibly increase the generation or possibly decrease the load. So at the grid level, the inertia of the equipment helped us also in another important thing in case of a catastrophic failure of an, let's say, transmission line or generator. We could possibly sense it and trip out the faulted equipment immediately. The rest of the equipment, rest of the system as a whole would coast along for a little longer before we brought in something else into the system and brought it to a stable situation. So that was greatly helped by the physics of the power system. We used to call it as N-1 criteria or N-2 criteria. So that in case of failure of an equipment, we all know that the power system will not go to a blackout situation or brownout situation. And we, as protection engineers, have been given a short time interval within which we need to isolate a fault and possibly bring in a new equipment, maybe an auto reclose attempt has to be made, or some auto changeover scheme has to be brought into picture, whether it is on medium voltage, high voltage, or extra high voltage system. So that's what we have been doing. Now, at the distribution level, I would say that the feed was mostly radial. Right? We have a power transformer, possibly let's say 132 kV slash 33 kV power transformer, 20 MVA or 30 MVA transformer, and that was feeding the system. And the system was radial. There's no major issues with isolating the fault with respect to a very simple overload protection aided with some of the instantaneous protection and differential protections. And another important matter we have to remember is also that all these years, we control the generation to follow the load mostly. We could possibly predict the load in advance based on the time of the day or the season, or we could also based on the other parameters, except when you have real situation and the generation of the grid for some reason, we need to resort to load shedding as a last resort. I would consider as a protection action rather than a control action at this moment. But by and large, the generation could be controlled. It could be either a thermal generation or hydro or other backup generation. So moving forward, we have a slightly different scenario is evolving. We all know that. I don't have to insist more on this particular aspect. We are talking about more and more renewable energy getting integrated into the grid. So what is the big deal about it? The point is that the renewable energy is not something you can control or you can alter easily. Having invested so much money, everybody wants to take the maximum out of the investment. So also a solar investor or a wind investor, and then he has to make money when, like I would say, when the sun shines or wind blows, right? So we have a situation, very interesting situation now, when the renewable energy has to be maximized in the grid. That's the way to go green. And at the same time, we have a situation, it is not always available 100% of the time. So this is fine when the percentage of the renewable is small, but moving forward, we have a major power generation being contributed by renewable. We are talking about 100% eventually, maybe around 2050. So naturally, things are changing very rapidly. So what are all the challenges? We all know that solar energy has no mass rotating, or it has got zero inertia unless you do some artificial thing to emulate, simulate inertia. We are nowhere there. It is just nothing but an electronic inverter. Wind may have some small inertia, but technically it doesn't exist. But then also we have the inverters, the power electronics, they're all sized in such a way that you don't want to spend too much money on investing the power electronics. They're quite expensive even today, standards. So whenever there's a fault, you want to protect those power electronics. So unlike earlier cases, when there was a fault, my synchronous generator would pump in at least with the generator transformer in tandem, they would pump in at least 3 times cycles. That is not possibly the case with more power electronics dominating the scene, right? So another interesting thing that has happened on the distribution side is that it is no longer radial. It has become more like grid. You and me want to put up a solar plant on top of a roof, and we want to generate and consume it locally, and if possible, we want to export that power. What is happening at the grid, the system level, is that your distribution become a problem. They have been designing all the cables of the system for rate. Now somebody has started pumping power into the grid. So possibly the power reversal has happened, for which the protections have not been designed. Neither the conductors have been designed always to take in the additional generation you are feeding in. So technically a complete revamp of the system, plus we can't afford to put all the protections whatever we have been thinking of in a grid level, let's say 765 kV system. So it has to be consistent with the voltage and power level we're handling. So it's a different ball game. And we all know that quality of distribution power is more and more of concern today. All of us have become prosumers. We want to look at how many times my power got interrupted, how long it got interrupted. There are different ways that we can attribute, and we can possibly even penalize the distribution company for that. So with all this, and then we also want to add the storage, which is last straw in the whole scenario, and it to bring in bridge intermittency of the renewable energy, but we can also use storage to reduce the peak flow in the system so as to reduce the maximum power that flows across the grid. All this means that we have, okay, I'll just skip this thing in case you want to have a look at it. So this is the lower current you may have with fault in a grid system. So what is happening today is that we are also looking at DC being another important element of our whole system. We all know that HVDC is playing a major role. We are talking about a country like India or US, a very big geographical region. We can pump power from one area to the other, 2000 kilometers or 1000 miles across, with possibly less than 1% losses. It has been made possible using HVDC. And if you remember, initial stages, I would say 1900s, these two guys, we all know them by name, right? Edison and Tesla. They had a big fight. One person, Edison wanted to promote DC, and Tesla was going after AC. General Electric was supported by or started by Edison, and Tesla was hired by Westinghouse. So these people had a very big fight. I think it's like watching a movie, I would say. So I think somebody has made this slide as if it is a Columbia Pictures kind of poster he has made. But today, of course, these two gentlemen are not those two. I can tell you some two old men, about maybe you can consider them as 2 or 3 generations down from those generations. We have AC and DC coexisting in our grid. When I use the term grid, I'm not differentiating whether you are talking about 800 kV or 200 kV or even 15 volt in a house. We have standards today for DC distribution, even in the lowest voltage system. So moving forward, we'll have all these things. So protection engineers today, they don't deal necessarily only with AC system, but also we need to deal with DC system eventually. And we need to understand the interaction between the two systems. And accordingly, we need to equip ourselves for applying protections either in the DC system or an AC system or in the interconnecting AC-DC systems. So this is just a small input I want to give for those of you who are very young and energetic to learn quite a few things, how HVDC is done in our power grids today. The major systems are all dominated by thyristor-based systems. We are talking about gigawatt levels of power transfer, and they're all very long distances. Still, it is quite economical to implement this kind of thyristor-based. converters. And when it comes to lower level, like hundreds of megawatt and shorter distances, we have started implementing quite a few modular multi-level IGBT based systems. So these two are already there. But moving forward, there are some disadvantages with the thyristor based system. I'm not getting into the detail. They draw heavy reactive power from the system, whereas the IGBT based system can technically even generate reactive power that you may need on the AC side of the power system. So there are advantages. But today, it is both, I mean, what do you call the economics plus the losses might be more on the IGBT system, but we are getting there. I'm sure maybe 5 to 10 years from now, we will deal with more and more IGBT basis. So I just wanted to highlight this so that the protection engineers are all quite aware of how things are evolving so that we prepare ourselves for those kind of systems. And another important thing we need to know is even in existing AC systems, you want to pump more power through the line. A very simple solution would be a series compensation for very long lines. We have implemented in quite a few lines across the world. And this is another system which is also getting in vogue more and more with power electronic prices dropping by the day. And we are going to have more and more of this. And this is also aided by the fact by better communication, better infrastructure, what do you call logical processing capabilities increasing. So we are going to have a mix of AC, DC, and these kind of solutions getting into the system. So we need to be prepared for that too. So what is the solution? Smart grid, right? So it's very easy to answer, but is it happening in a big way? Today, I can see that you use the term smart grid. A lot of utilities, they more or less use it in the distribution system, especially for the metering. But we need to possibly look at more and more of this with respect to our power system operation control protection on those aspects also in a bigger way. The grid level, we have put in place a lot of communication automation and all that, but more and more of this will happen at the distribution level also. And the energy storage would be another important element. We all know that batteries are playing a very visible role today. I would use that term visible because you find that hundreds of megawatts of battery is getting added into grid, whether either for peak shaving or for so many other reasons. But the mainstay all these decades have been the pumped hydro. We all know that. I mean, I'm not trying to get into the details here, but pumped hydro, they have their own issues. I mean, we cannot have a pumped hydro in a desert place, or we cannot have it in highly populated locations. So pumped hydros are there where it is feasible and economically, ecologically possible, we will do it. Otherwise, I think possibly we are reaching a stage when pumped hydros cannot be increased beyond a particular limit. And so we are struggling today at the grid level. Let me use that word, struggling, to get economically viable storage in the grid, both at grid level as well as at the individual distribution level, so as to make a full integration of renewable energy into the grid possible. I would say today, if you ask a country like India or Saudi Arabia, I think NEOM is an important project. We all know it's coming up in a big way, but the challenges could be that we don't necessarily have a high level of competing storage technology to go along with that's where I think we may have some stumbling block, but we are all humans. I think we know how to work around these issues and you'll definitely get that. And so this is what I would definitely say that storage is an integral part of storage future grids. So when you talk about protection, we need to talk about lines and transformers, and tomorrow we need to also talk about more and more about protecting the storage element, whether it could be electrical, mechanical, or whatever form it may eventually it may assume that will be there. I think this is also another integral part. Now, this is another interesting slide you might have seen already. Whether we can avoid storage by taking advantage of the fact that sun shines, as I said in the very first slide, right? That sun shines at least 50% of the earth any point of time. So if only, let us say it is bright sunshine in this part of the globe, eastern part, and it's going to be a night in the western part of the globe, I could pump power from east to west if I install necessary capacities to solar, and I build all this HVDC or any futuristic technologies that might evolve to pump for power from one side to the other. So I don't have to really worry about storage. The answer is yes and no. The point is that the cost of installation plus the losses in transmission, that is on one point. And the second point is that how expensive is the storage. So to us, it looks like it's going to be a combination where the distances are huge and you have sunshine across east to west over a large geographical location. HVDC could possibly reduce the need for storage, but in a small and geographically short radius, storage would be a solution. Again, in my opinion, both would coexist. And then, of course, microgrid, it could be either connected to the grid or it could be an isolated system like in an island system. And we have all this equipment coming in. So electric vehicle is picking up. Technically, we are shifting uh, the gasoline or diesel energy supply chain from what they are today into electrical system. And electrical system means you can integrate the renewable energy. That's the biggest advantage I see, more than reducing the pollution and other things in the cities. The bottom line is that we are making the transportation greener by going for electric vehicle charging as part of our grid. And to that extent, we have more and more, let us say, EV infrastructure getting added into various parts in the globe. And along with that, add the storage to an extent, your rooftop solar at the distribution level, and at the grid level, we talk about offshore wind or desert gigawatt levels of solar energy from the deserts, they all get integrated. So what is microgrid at the smallest level would be a grid level thing, but the picture is more or less the same except the scale changes, right? So this is something which we should possibly appraise ourselves and study about how to do a fault study, how to go about applying the right protection, what are all the communication infrastructure you need to put in place so that I'm able to isolate a faulted section very quickly. So how to protect the evolving grid, right? So this is something which is happening already. We all know that we have multiple solar or wind power plants getting added. There could be a long line from a solar plant to my grid. Let us say it's a double circuit line, and naturally, if you look at the distance protection, as we know all these years, suddenly we're ending up a situation where the distance protection may not operate for a fault in the line feeding from the solar power plant to the grid, right? So that's a bottom line. So we are talking more and more about differential protection could be one solution or could be an adaptable solution. So this is something which I thought I'll just share, just a little bit of humor here. What we learned from our evolution on this planet, right? Same thing is going to be applicable for our protection engineering also. So we need to make it adaptable. We all know what adaptive protection is by and large, but we need to take it to the next level. For those of you who may just want to quickly know what it is. So this is what the point is. Conventional protection relays, they act very fast, but the information additions are localized, right? So they mostly do not have system-wide information to adapt themselves to changing system conditions, like power swing. There have been quite a few situations, like when I was very young, I used to set this power swing protection for some of those old UPSCB that time or MSCB. They would trip unnecessarily for an external system disturbance. System was very weak, and we used to have blackouts quite often because power swing would possibly detect something and then trip a line. That was a very, very bad scenario, but things have evolved. And today we are in a situation where we have better information about the system, and we are able to bring in those systems either automatically or manually to make changes in our protection settings. That's what it is all about. So we have from IEEE, it is about adjust settings of protective relay to the prevailing conditions of the power system. So this is one important element which we need to do. And naturally, how to make this adapting the system, protection setting automatically. That is another interesting thing. That is where I believe this smart grid system with communication and other background infrastructure would be very, very critical for us to say, I'm doing a proper protection for the system. So ultimately, what we need to achieve is that to increase the overall operation efficiency of the system. One thing we should also remember is that in the good old days at DHV system, the protection engineer role was very, very critical because in case he didn't do his job well, blackout is more or less certain. Okay, so we need to make sure that the protection operates in maximum maybe 2 cycles, and the breaker should trip in 3-4 cycles maximum, or 2 cycles typically. So less than 100 millisecond, you open the fault and give another 100 millisecond or something for the fault to recover. Maximum 200 millisecond is the time we are looking at. But today, the ball game is changing, right? With more and more renewable energy, better control, the bottom line of what we understand about what protection should do may also change from system to system. That is something we need to understand. It is not a single rule which we need to follow as far as the EHV system is concerned. On the low voltage system, again, the simple overcurrent time grading may not work anymore. We have power flowing here and there and everywhere, and we need to make sure that cables don't get overloaded, in addition to making sure that protection, because earlier the loading was done in such a way that the cables don't get overloaded. We're not bothered about it so much. But tomorrow we need to make sure that we have the settings, and we have to make sure different scenarios we need to look at, fault happening in different places depending on weather conditions, whether this solar energy is going to be in place, what is the fault current. So a fault study and other things are going to be much more complicated. We need to have multiple scenarios, and based on the multiple scenarios, we need to evaluate what would happen to my protection system, and accordingly we need to set the protections either manually or automatically. That's all. These are all the changes that are challenges that are coming in. So if you remember, in the distance familiar with the Mo, we used to call a thing called expanding Mo characteristic, and the quad characteristic, the top line would tilt to adjust itself for the resistance depending on whether the load flow was in the forward direction or reverse direction. And we also used to have voltage dependent overcurrent protection. All these things had a certain element of adaptivity automatically inside in themselves. Even in the static days, static protection days, we used to have it. But tomorrow, with better processing capability and other technologies in our hand, we can foresee a situation that distance characteristics, let's say what is quadrilateral, could become totally oblong shaped characteristic to cater to faults from the renewable generation, which may tilt or alter the fault resistance in a totally different way. So these are all things which we have already done. Quite a few papers and quite a few PhDs have been done on these topics, and we have necessary information today to go ahead and adapt the settings in such a way that we can take care of all this. So we are getting there slowly. So I'm sorry, went back there, right? So the total approach, as I said, on the right side, system study, that's where I think we need to equip ourselves to do better system study and make things look better for all of our setting parameters. Now, this picture could be, 1 second. This picture is very interesting. I'm just trying to again go back to how things are evolving. The what do you call the domain principle? The time domain principle is what is evolving today compared to what we call as frequency domain protection. I'm just trying to highlight. You might see that on the left side, it's actually an induction motor, right? So why am I not necessarily induction motor? It could be any induction machine. I would use that term in general. Why I have shown it is because this is the same principle with which our old induction cup or induction disc, not disc, the cylindrical protection, cylindrical cup relays operate. They know basically they are supposed to check the phase sequence of two signals, whether one signal is leading or lagging the other. The induction motor is a very simple machine in which you reverse the phase sequence A, B, C, instead you give A, C, B, the machine would automatically start running in the opposite direction. So technically, it is a very intelligent device wherein, based on the phase sequence, it is able to decide whether to go in one direction or the other. It doesn't have any algorithm, it doesn't have any mathematics inside, but it's a basic fundamental physics behind the induction principle, which helped us do that. Same principle was in our induction cup relays or induction cylindrical relays. That's the earliest time domain principle which we have adopted in our protection relay to start with. When it comes to the static relays, we try to somewhat simulate what we were doing in the electromechanical relays. We used to have amplitude and phase comparators. If you know dual, there is no major difference with respect to the principles are concerned. Amplitude comparator can be equated to a phase comparator on the other. And in early 2000s, when I was the product manager for this product, which you see on top, which is a ABB relay. It used to simulate a induction cup relay. It was taking converted them into digital, but inside it would use the physical principles of a cup relay and accordingly to decide the fault is inside the zone or outside the zone. That was one of the first few uh, time domain protection relays. At least I have had hands-on experience with that relay, and we used to have stripping in 500 kV systems in within 2 to 3 milliseconds. It was a static output relay. We used to detect faults very fast. At the same time, we had made it a little bit too I would use the term slower faults so that it doesn't misoperate. So there was a point beyond which you couldn't do much in that protection. But today, I have just projected one Schweitzer relay where they claim that they have one of the fastest time domain principled protection relay for distance protection. So what I'm trying to say is it's not about the manufacturer, it's about the technology we are evolving into. And eventually, I think we'll have more and more of this kind of technologies that are coming in. But for those of you who want to quickly understand what this frequency domain and time domain are, this is what we have been doing. So in a frequency domain principle, we basically take a waveform and sample it over a full cycle and pass it through a filtering algorithm. How it operates, if you multiply it with a standard sinusoidal waveform of the same frequency, it would generate a signal in the positive direction. I have put the right side picture just to highlight. If you have current and voltage waveforms exactly in phase, the power is always unidirectional, correct? So it is positive. So you are able to say power is equivalent to I into E instantaneously. But if you average it over a full cycle, it would be a positive value. Same thing has been done in a typical Fourier filtering. And you can say that when the current and voltages are 90-degree apart, the power would be zero, correct? So also in the left side, it can, by multiplying it with another waveform at 90 degrees, we are able to get two components, the real and imaginary components. So we are able to get to the phasor value of the incoming analog waveform. So this is how we have been doing the basic Fourier filtering algorithm. Typically, an ideal Fourier filtering algorithm cannot fully eliminate all the transients like DC transients, but it does the job fairly well for most of the applications. And what we do today is that go a little bit further. We go for what we call as quarter cycle, half cycle Fourier filtering with some limitations. We are trying to make the whole system faster. So this is just a three-dimensional application or characterization of what is in the time domain and what is in the frequency domain. We all know that any signal in the time domain can be taken in, can be resolved into multiple frequency domain based magnitude and angle. And moving forward, we have today in market traveling wave fault detection, which can detect fault. It can trip a line, or it can also calculate distance for location. So there are some algorithms in distance or time domain based, frequency domain based algorithms also, but this is what is evolving. So I just wanted to highlight. So this is being marketed in a big way today in the industry. But back, I cannot forget those days when I started my career, or even earlier when I was in the college. I did a project for my final year engineering degree course based on what we call as a directional wave, traveling wave protection principle. It used to trip in 2 to 5 milliseconds. So that was marketed by ABB. It was not successful for various reasons. We have Schweitzer again coming up with multiple things. G also has similar products. I'm not trying to possibly highlight any particular vendor, but this is how things are evolving. So traveling wave is another evolving technology which is helping us detect and isolate or locate a fault in a power system. This is something I just want to highlight. So the next interesting thing that has happened, again, it's more than 20 years old technology, but slowly it is finding its footing in the utilities, is phasor measurement unit. So what is it so special? In this phasor measurement unit, unlike an individual IED, which are geographically separated, the phasor measurement unit has a common time stamping across all the individual IEDs. So in case you measure voltage at particular point A, I can also measure voltage at particular another point B, maybe hundreds of kilometers or miles away, and say that A and B voltages are 1 millisecond apart or in degrees, 10 degrees, 20 degrees apart. Why is it important? This way, I'm able to measure the phase angle or the parameters of a power system without necessarily going through the earlier approximation or estimation of the state of the power system. I'm able to measure it very accurately. Once you measure the phasors very accurately, I can technically predict various flows, or I can also confirm that the flows are in order. I can even use it for eventually any issues with the system as a whole, oscillations. I can use it for taking preventive action, because if in the next slide you would see that if you look into the right side picture, you will find that the horizontal axis is the time and the vertical axis is the coordination it takes. You find that the SCADA takes a few seconds to update itself. Protection relays, they are mostly local all these years. So they take the local information within 20, 30 milliseconds, they trip. There was a big gap between the SCADA measurement, operation control, and the protection instantaneous tripping for equipment. So the wide area measurement monitoring systems, they fully fit into the intermediate region, and that is what has been helping the system. It has been implemented in multiple countries today, but we have to develop multiple applications based on this input. So that is also another evolving area wherein we talk about the protection possibly gets not only limited to the lowest corner end, what you see here, a lot of things will move on to the wider area based monitoring system with protection. So this is just a quick picturization of the data flow. Of course, I would never say that the protection at the local would ever go. No, it is required, right? So you need some kind of processing element, which should definitely look at, let's say, transformer differential. I don't see any need for sending the information all the way up the cloud and doing something there. At this moment, we have quite a few interesting things, very fast and proven things, which are happening at the local level. They'll continue happening, but we will enhance them with wider area system as well as other cloud-based control protection automation. So feature grid, I think this is something very just to relax your minds a little bit. So I don't ask me who this Yogi Berra is at this moment. So it is tough to make predictions, especially the future, right? So we cannot predict anything. You and me have limitations. We cannot predict anything. But what I like is this statement from Abraham Lincoln. So the most reliable way to predict the future is to create it, right? So you and me are here. We are building the power system of the future, especially the young ones. I would request them to take it as a challenge. So don't keep on predicting something in future. You build it. That is the simple direction I would suggest. And so a few things which cross my mind often is a few things which might also excite you is the relative improvement in the superconductivity, correct? So you can see this graph. This is the normal metal, and we have a superconductor, virtually zero resistance up to a particular temperature. Right now, this temperature TC is not really usable by us. It is right now they're talking about room temperature, superconductivity, and all that. But let us assume that we are able to push this TC to a level at which I can start laying conductors for my power system at room temperature or slightly even at elevated temperature that we experience in most of the countries. I can pump thousands of amperes at maybe 5 volt or 10 volt. I don't have to step up the current, step up the voltage. I don't have to do anything major. So the whole power system scenario may change totally. We all agree? So this is something for you to look at. So possibly superconductivity and other related technologies might also help changing the power system we know today. So what is shown as a big conductor may not be needed at all. And blockchain technology, I've just highlighted one tip of the iceberg. The digital technology is also going to make a major change in our power system. And naturally, the behind doing whatever they have been doing all these years, we need to update ourselves, apprise ourselves of things which are evolving. And I would suggest we need to do a little bit more on blockchain technology, and then the cyber security stuff, typical things which are very essential for running the power system. We should arm ourselves with. And another interesting thing that is happening is that I can see today things like hydrogen is also being used for storing renewable energy, because right now as I said, we lack the storage technology in a commercial way. So I find that people are talking about hydrogen and ammonia. I know in Saudi Arabia, they have given an order to a company to generate ammonia from renewable energy, and then they are shipping it out to other countries. It's happening. But how big it is going to be, I cannot predict. But definitely, these are all things which we need to keep our eyes and ears open. And having worked in ABB, I know we have a special cell which is working in this technology. But what we had seen that point of time is that we will help in doing this from the electrical power system. We cannot totally avoid this. We cannot say this will not happen. We feel that this will happen, but what is important is to make our electrical power system on the left side and the end side suitable for this. So let's prepare ourselves also for those kind of stuff. So I should take this opportunity to quickly thank all of you for listening patiently all this time, and Mr. Selvakumar Power Projects for giving me an opportunity to interact with you. And I have referred quite a few resources, both online and offline. I assume I have acknowledged and referenced most of them. One or two I might have missed, but I suggest very strongly you will be given a handout, but really suggest that you don't use it without possibly referring to the original source. So they are not necessarily free copyrighted materials, some of them are copyrighted. And I also thank my teachers, mentors, colleagues, students, and especially the younger colleagues who used to interact with me. That was the motivation for me to learn quite a few things. Thank you much for that. And as I said in the very beginning, I don't want to talk much about the technicalities, standards, and equations, but I have just added a slide. I like this slide because it summarizes a lot of things which applies us eventually. And some references I had given, complete again, but definitely we'll look into it more in detail based on your inputs and queries. And we are now open for discussions. So I would request Mr. Selvakumar to take over and take it further. Thank you.
First question from S. Namburi. How blockchain applications in power system protection? I guess like he wants to know more about this blockchain applications in power system, sir.
Okay. The point I'm making here is that the blockchain, as we know it is a technology which is coming up in a big way. And I think it may have find more application in the distribution system, especially microgrid, right? So when it comes to microgrid, let us say you and me want to exchange power. Like they say it is the power also will become like our internet. We are talking about modules of energy getting exchanged back and forth. And unless the production engineers keep track of how things are happening and evolving, I'm getting into a situation where I don't have an idea about how the power system exchange takes place. Okay, I don't say directly the blockchain will be directly used in the protection. I'm not envisaging it at this moment, but very clear understanding of how things operate would be very essential. That's what I was trying to highlight here.
Yeah, thank you, sir. Thank you so much for that. Let's probably take a few minutes. There's a question from Syed. Does in future we also possibility of connection of the fault current limiters like reactors at the distribution energy generation side?
Absolutely.
Means,
Absolutely. We have quite a few situations. I think we do have a small device, looks like a fuse that has been applied. You want to extend an existing switchgear, which if you add one more transformer to the switchgear, you might exceed the short circuit limit. So we have successfully in some cases. Now, when that is getting applied, we can definitely even putting a reactor. But the problem with reactor is that may have continuous loss in case you want to keep it in service all the time. So we could think of protection possibly coming in with along with the high-speed fault current combinations could be used in future.
yes, thank you so much, sir. There are like many methods of fault current limiting type is available, and of course, current limiting reactors, IS limiters. There could be many choice. Like
I didn't want to use
said,
I didn't want to use
yes,
the trade name. I'm not sure
right,
who
right,
else
right.
is facing it. Yeah, thank you.
Correct. Sir. There are some other companies also has
Yeah,
similar
I know.
products. Right. So means what is it? The option is wide open. Like I mean, as sir has told, means what's the technology which is most adaptable will survey the future. Yes, and I guess like few people have asked this question whether this webinar is available. So, means this webinar is available in the YouTube channel. What we have, it's currently is also ongoing, and the slides are available. And I have shared that link in the LinkedIn post, so which you can take it. So, and probably let's take one more question from Sayed. In case of distributed energy generation, can we adopt the feature of the deviation of power frequency component before and after fault in relays instead of adaptive relaying or setting changes? Which means like if you want to like measure the frequency deviation for this protection instead of having this means what's means what's the different stops.
That question comes with quite a few conditions. Like when you are connecting grid, I wonder whether you'll have major deviation. I assume that the question is for a small islanded system, right? So that is a thing which you could possibly simulate, because I don't see a major frequency variation happening when you're tied up with the 220 kV system, let's say, for example. Assuming it is for the distribution system, yes, the frequency deviation could be one of the measures. I would suggest study that before you conclude either this way or the other way. I think it's very difficult for me to answer such a question unless I know the system. I think Solokumar and team can possibly do a simulation. And honestly, I always believe that a few things cannot be predicted unless you do a. I think this question for that. So I think it's a question of take some of the typical critical parameters in the system, and we can definitely look at that. I don't see any problem in that otherwise.
Yeah, thank you, sir. Thank you much. And as you rightly pointed out, I mean, I would say the change in the system frequency is just not depends on the renewable resource. Like it depends on what's the total installed capacity, what's the load at that moment, the percentage of renewable concentration at that moment. Like there are plenty of factors behind it. So, and probably means there is a fall, like how the frequency changes also depends upon quite a lot of dynamics. So maybe the future we can probably predict and probably we can have a protection. But as Sar has rightly told, you may be able to use that or implement that at least for the large scale systems. Maybe for a small scale systems where like your fault current is almost close to the load current, and there probably you can apply some concepts. But for a really a large grid connected system, such necessity it doesn't really arise. And probably one interesting machine, like guess Karthik put up at like very early of this presentations. I guess like you covered also as a part of that in your slides. Do traveling wave protection is mandatory for a transmission line, and he sees only this. I mean, so ACL and probably means some recent Siemens relays have this feature. But like I mean, so say his experience, like he has commissioned quite a lot of other protections without this. I mean, so say traveling wave theory. So what's the your call, sir? Traveling wave protection, future of traveling wave protection?
Yeah, I think that would be an important element at this moment. Bit difficult for me to predict that will be the only thing which will exist in future. That is, I would say no. There will be conventional protections also there. They have been doing a good job. Distance protection, for a fairly long line, I would say the low SAR systems. As I said, we have been able to detect within a few milliseconds. We can definitely go on that. And along with a couple of other things, what I see is happening is very interesting, like traveling wave, right? So it's for EHV system where we may experience more and more lower fault levels and other things we don't know at this moment. So it's hard to difficult. I mean, it's very difficult to predict. It will be definitely one of the components. I mean, that's all I'm trying to say. So don't lose sight of the conventional protections, whatever we have been using all these years. So open your eyes in case in that direction. Yes, you do go in that direction. So I cannot predict at this moment how things will evolve.
Right. Right. Thank you so much, sir. That's very true. In fact, like even 2015, I thought like microgrid will never ever work, and probably
in future AC systems also. So IEDs may all merge into possibly one or more equipment in a station. I don't see any point in shifting it to the central location. I think it's totally disaster if that goes and sits in where you have a fault in Riyadh, and if the system sits in, let us say, London, and if communication breaks, you are not going to have the local breaker tripping. So the point is that we need to have a certain amount of things which will happen as a first level defense. We need to have a guard at each level. There is no shying away from that fact. So that will continue. At the central level, a few things which we cannot achieve sitting at the individual station level or substation level or switchgear level, they have to happen at a regional level or country level or even at continent level. Those things can also happen. And as you go higher and higher in the hierarchy, the slower and slower it could become. But that is sufficient. Like, let's say oscillations may happen in a few minutes in a power system. You don't have to really detect it sitting in a substation. You need to look at a regional level. Those kind of things, like what do you call this substation automation system at the lowest level, and possibly the grid level supervision, along with the phasor measurement system that would be in place. Already happening actually. We talk about system level protection are already been implemented. At least in India, we have quite a few of them implemented by Power Grid. Let us say HVDC line trips. Immediately, you want to shunt out some of the load to other systems, or increase start new generation. All those things are already happening, and they don't happen in a few milliseconds. They may take a few seconds before things happen in place. The idea, the bottom line is that to ensure continuity of the power supply to the ultimate customer, right? So that is what we are trying to do with all this. So sometimes you get very limited time, sometimes you get adequate time to do a few things at the center. But yes, central, it's a little bit vague to define at this moment, but I would say we may have central equipment, usual substation level or switchgear, but we need to have at the grid level, or let us say an area of let's say distribution utility, right? Utility may have a common city level protection or system level protection system residing in the supercomputers at the city level that might take care of quite a few things on the city side. And similarly, at the country level, you may have grid level automation and protection. That's what is the eventual direction I see things are going.
Probably means what say. Means my view is like means power system is becoming more and more decentralized, and is going to probably more centralized.
Yeah.
So, but the drawback, like rightly what sir has said, if you go the protection, move the protection from means what's the individuals to centralized, then time delay is the only thing which you need to take care. Like if you
reliability
take
is another factor. Not only time delay, maybe you have perfect thing, but then any element. I mean, we want to make protection simple and stupid. I use the term stupid here to make some. Normally, we say when a person is very simple, we think he's a stupid guy, but protections are not stupid things. I think we have had the most smartest system in the world for more than 100 years now. That's what I take pride in. What power systems I've been doing. We are adding more and more intelligence. Doesn't mean we are definitely becoming smarter, but it is not. It makes out people are trying to make out things as if we have become smart just yesterday. No, that's all I'm trying to say. We have been smart all these years. We are making smart. So I would use the term smarter grid. If we had invented that, coined that word, I would have been happier. That's all I'm saying here. Yeah.
Great. Even probably means what say when I have visited some old hydro plants which are more than 100 years, like still the old electromechanical relays are still operating and they are happy with that. So
absolutely,
as long as it's meeting the purpose, that's great. Thank you, sir. Let's move to the other question from Makesh. Pumping power, I guess, like he might be meaning maybe pumped hydro. Pumping power concept across the world is now existing. Maybe because now everybody hears the word battery energy storage system, so his doubt might be like pumped hydro.
I would say the pumped hydro has been the mainstay. I don't know the exact number. I would use the term something like 95%. Okay, just to impress upon this audience here, 95 to 96% of the storage that is happening in the grids today are still pumped storage. The batteries maybe you can say 2-3% today maximum. Even that I would be surprised if it is. But pumped hydro have been mainstay. They have been, and also the way we control the hydro plants, that's another interesting thing. All hydro plants, even if it is not pumped hydro plants, we have been throttling the power flow to adjust the load flow in such a way. Let us say we have the backup storage available. We have been very judiciously using it as a kind of a storage device also, indirectly. So it's a combination of hydro power plus pumped hydro storage, which has been to our help all these years. To a little extent, gas plants and other things which are fast acting and fast startup, those things have also been helping us. Not the thermal plants, not the nuclear plants for sure. It takes minutes, if not hours, to change their power flow. So this is the mainstay. Now today, tomorrow, today, yes, batteries are it costs fees per kilowatt hour for a hydro plant. I can give you that number roughly. Whereas it costs more than today, I don't know, maybe $200, I don't know, per kilowatt hour. That's the cost of battery storage. So it's nowhere near what I would like to do for my grid storage. You may be able to afford it. That's a different matter. But comparison, it pales in comparison. That's all I'm saying. Possibly the battery storage cost would get added to the renewable generation cost eventually. You know, no longer that 2 rupees, 3 rupees cost we get from solar. It doesn't give you a true picture actually. If you add even 5% of that generation towards storage, the cost will go up. Because that's essential if you want to have higher levels of integration of solar into the grid.
Right, that's right, sir. Even if you take the case in recent India, the SECI tender, like 1,200 megawatt renewables plus energy storage they have called for like peak hour, and out of which one of the vendor is proposed. He won the bid like with 900 megawatt based on the pumped hydro, not really based on the storage technologies like what we are talking.
No, we are not there.
Yes.
Believe me, we are not there. It would be much more expensive. Yeah.
Right, right. True, sir. So probably that's what, like, there are quite a lot of puzzling words which are going around the media, etc. I'm not really against the battery energy storage system because I'm working in battery energy storage systems for the last 6 years. But at the end of the day, we need to honor that may not justify.
That's true. Yes. It may be cheaper to do some other technologies. That's
yes.
Also true.
So then one of the questions from Ramakrishna, what will be the impact of harmonics being injected due to the electric vehicles, solar PV? Like everybody is talking about the renewables, solar energy storage systems, electric vehicles, all the stuff. So all are powertronics. Harmonics are being injected. So what's the impact on this production?
Yes, it will have a very interesting impact. That's why I use the term. How much effect it will have on the protection is the answer. If you want, it may not have so much effect. I think we will try to limit the harmonics under normal conditions, and during fault conditions, definitely there'll be a lot of harmonics getting injected, and possibly I would use it as a signature. I'm just thinking aloud here. You inject more harmonics, possibly the harmonics are highest to the closest to the point of injection. We might use it to our advantage. We don't know, right? So there have been cases like I remember long back, the third harmonic voltage, what we used to get from the generator neutral, the neutral side, we used for detecting ground the neutral, right? Just stack it up, but a good way to detect, like the way whenever you design a system, it is easier possible to protect a high fault current system than a low fault current system. Same way. So if you limit the harmonics to a minimum level during normal conditions and you happen to inject higher harmonics, maybe that's one way. Interesting question. I don't. It triggers my thoughts and imagination. That's all I can say. But it is not going to harm you in any way for a short time during fall condition.
Yes, sir. Thank you so much. And probably some means what to say. Mahesh, he has interacted with you in 2008 from a big independent power producer. He's conveying his regards.
Yeah. How are you, Mr. Mahesh? Yeah.
And Dijo, like he's our head engineering and design. He is probably putting his thoughts not as a question. Like a good production engineer should be a good communication engineer too. So like without communication, your production, that's great thought. Thanks.
Absolutely, absolutely. See, those days we used to be in silo. I mean, we used to keep those SCADA guys away from us. We used to have a separate box for protection and separate box for event recording, fault recording, annunciation. That is not my baby. You take care of it. Slowly, the IEDs brought in a level of integration wherein we couldn't avoid them. And of course, we used to say the power line communication is the only communication guy where we used to interact with. That was the only thing which was directly or indirectly tied up with my protection. We never used to bother about other things. Slowly things have changed. We started using RS-232 port and ASCII character for setting changes and all that. Slowly we have become communication experts. If you ask me whether I'm a 61850 expert, no, but I know what is going on, and to that extent you learn. a few things, and it doesn't matter. It helps you because I think today we cannot separate out protection from communication with a very clear demarcation line anymore. So I would use the term somebody else has asked, including, as I said, the blockchain or Ethernet, whatever things which are going to help you in protecting a system. You should be very aware. If not, you are an expert, you should be very aware of what is happening behind it. So the idea is that you should drive the communication, guys, not the other way around. That is what I am trying to drive at, because we are ultimately we are protecting the system. That is number one thing we need to do anything in a power system. Please don't allow that. So no things so that you drive those guys around. You say, I want to have this signal within 3 milliseconds, 5 milliseconds, or 10 milliseconds. This is the reliability I want. You monitor, control, and protection engineer.
Yeah, thank you so much, sir. Maybe we will take 2 more questions and we will wind up.
Now, so long as the audience are okay, I'm okay with that. So no problem.
Thank you so much, sir. So this digital substation nowadays, that's also a talk of the day. Digital substation, like, I mean, what say, if cyber security fails, like, then like what's the adverse effect, or probably means how do you see the digital substation and cost of this digital substation? Yes.
Okay. There are multiple questions. First, I'll talk about security. It's like maybe 15-20 years back, I don't remember. I was very afraid of using my credit card, right? So I thought somebody would steal your information and you just insert that thing, even ATM machine, even today it's happening. So there's a certain amount of risks in whatever we do in life. That's what I'm trying to highlight. So when you go for anything digital today, and we are bound by digital, your SMS, and I know many ways people are all hijacking your information and taking advantage out of you. So also in a digital substation, definitely it is vulnerable for cyber security or cyber related attacks. So we need to guard against it, and always the thieves are one step ahead of you. That's the thing. We need to learn a lot from them. So try to do a few things in which you are ahead of it. But in case you are so ignorant or you are not careful to let the system be taken over by a cyber thief, I can only say sorry for you. I think what can happen is a question of somebody tripping out a machine or tripping out a line, causing blackout. I mean, that is a worst case scenario. Anything could happen. I don't know. See, we all remember, 2012 was it? I don't remember when we had the blackout. What happened on zone 3? Element tripped for power swing or something like that. It was getting overloaded and it caused chain reaction, like one after the other things tripped. So in a big grid system, if you let go of your security, it might cause a chain reaction based on, suppose you are a nuclear plant and somebody hacked into, or what is that one down south in Tamil Nadu, the new nuclear plant, Kaiga, not Kaiga, that 1,000 megawatt Russian plant. Yeah, somebody hacked in, Kudamukulam. Somebody hacked into it and they somehow managed it. But somebody hacks into a 1,000 megawatt plant and shuts down 2 units, it can cause a severe damage to the grid, right? So I can say if you're in an industry and you are running a process plant, and let's say a steel plant, and you allow somebody else to come and trip your incomer without allowing the DG or some backup to start, that also is worst case scenario. And you are going to have the whole plant come to a standstill. It may take days and months before you can chip off everything and then restart it. So that's the kind of thing. So you need to treat it very, very seriously. That's what I was in the R&D section. I used to inculcate this particular thing. View it very seriously. Whatever we do, it is not just bits or bytes. It's life of people, it's life of the equipment, it's life of the grid. So that's the kind of seriousness we need to attribute. And I think we as protection engineers, we are possibly the foremost to understand that better than anybody else. That's all I'm trying to highlight here.
Yeah, then thank you so much. That's like a great thought on this. And I guess like many people are still asking this recording sessions and slides. My suggestion is like, I mean, so to say, I have already shared this, but anyway, once again, I'm just going back to this LinkedIn. I have shared this link of this post. The slide is available in this link, and this means for the YouTube of this class is also available in this link. So kindly make use of it. That's just probably the update for all audience, those who are keep repeating this question. Like the recording session is available as well as this Q&A is also available. And with that, maybe let's probably take one more question on this. Like, let me take maybe one last question from anyone if there. Like, there are quite a lot of questions which are going. Like, I will take and consolidate all the questions. I have stored the chat, so don't worry about it. Like, we will answer all those questions probably after the sessions, right? And PUTT, POTT, these are all probably pure technical questions. I don't want to really, I mean, so say take that questions.
You can take it offline just to, because I think
Yes,
the
yes,
spirit of this
yes,
talk is
yes.
slightly different. Definitely, we respect the
Yes,
question.
probably
We can
that's
take it up
more specific
later. Yeah,
questions.
yeah.
Like generic questions, we will take it in forum, and more specific questions we can take it
I
off.
can read the question. What is impact of IoT in protection? Right? Is that the question you want to attack now?
So like though P2T is advantage over POTT scheme, why in India most of the utilities use POTT scheme? That
You want to take up now?
just above that, yeah.
Yeah. Okay.
You can take any one questions which you want.
No, I would skip the POTT because the answer is available everywhere. So I mean, with the permission of the question person who is asking Satnik, right? I'm not sure whether I pronounce his name. Satnik, I will get back to you on that later. So just to limit the time here, machine learning based protection in real time. If yes, which scenario we can use them? So I think I have briefly highlighted, talk about this medium voltage, high impedance fault detection. I won't use that word protection here. We have been using it for some time, since 2000 or even earlier. 1990s, we did the research as a community, I'm saying. So GE started and ABB did it, and Schweitzer have also done it. So here we are talking about the signatures, which is like high frequency, low frequency, and so we have taken it through an artificial intelligent machine. I would use the term, which is self-learning, and it learns from the past experience, and it's able to throw out a number, a probable number. It is not a certain 100% fault. So we are getting there already. And to that extent, if you talk about, I think I mentioned about equipment maintenance, DGA, let's say. DGA, if it goes above a particular limit, it's cause for concern. But then a combination of multiple gases, how it will effectively reduce the life, or what probability will have. So these are all the things which are what we call as artificial intelligence, machine learning, or big data analytics. Things are going on like this, and there are a lot of startups in this. Just to keep you informed, I think for those of you, this is an evolving topic. There is no definite yes or no answer to say that this is the best, that is the best. So any artificial intelligence stuff, maybe it will throw out some probable number, right? So this transformer is going to fail in 5 years. It may fail today, it may fail after 5 years. Whether it will be failing on January 31st at 9:30 a.m., I don't think anybody can answer that question based on the data we have. So definitely, if you want to, it's all question of reducing the probability of catastrophic failure in your thing. So if it goes above 90%, you take it out of the service and do some maintenance or filtering, those kind of things, so that the protection as such is getting integrated as part of the artificial intelligence thing. So the conventional protection, what we have based on this frequency, all those things, I see a situation when there will be a merger between what we do at system level artificial intelligence thing and whatever we do at the lowest level. And current voltages and all will definitely be a component. Unfortunately, with let us say fiber optic current transformers, I can do away with my transients so much. I mean, what I'm calling about the noise generated because of DC transients and all that, I can possibly filter out better. And CVT transients won't be there. Let's assume that. No, that helps me in getting at the root cause of my problem better than what it is today. And that is where I think I see artificial intelligence. And also as a distribution system. Let us talk about a distribution system. I mentioned about harmonics. Let's say you have a fault in the system. The harmonics may get generated by the inverters, even though the current is small. Let us assume, I'm just suggesting this, we do a study. From our simulation study, we see harmonics. You can study the harmonics across the system and then quickly say the fault is most likely occurring at this point, in this particular point in the cable. We could do that. You have to imagine your point first, and then you can work on that. That's all I'm saying. So definitely, the big data analytics and artificial intelligence will become part of our protection functionalities in the near future. But it's already happening in some areas. That's all I'm trying to highlight. Like like the high impedance fault detection in a medium voltage feeder, and possibly it will be extended into the low voltage feeder also, where exactly the fault is, fault location. That also can become a bit more intuitive with the artificial intelligence. Yep.
Thank you so much, sir. Like maybe let me take the last question before we wind up our session. And there are few more announcements are coming at the end. Please stay connected for that before we take the last question. Can we use machine learning based protections in real time? If yes, in which scenarios can you use them?
Okay, when you say real time, again, I need to define what real time is. As I said, within 5 millisecond, 10 millisecond, I don't see any of this artificial intelligence has that kind of muscle power to do a few things within that time. It takes possibly a few iterations, and when you talk about big data, you're talking about big, what do you call, the computing capability, which may take a few seconds or minutes or hours sometimes. So as of now, the real time, when we understand from protection engineering perspective, is in less than a cycle or 2 cycle maximum. Maybe in the distribution system, maybe maximum 1 second or 30 seconds. That's all the real time protections as we understand as protection engineers. But in future, definitely real time, when you are extending it, possibly the capability of computation also becomes better. Then we can have definitely real time things. But when it comes to the system level protection, SPSs or whatever, if you consider that as real time, yes, we are already doing it. With a little bit of artificial intelligence is getting added at system level, we are already doing it a little bit. I mean, I don't have the details, but we are there. Maybe a few minutes until we can do that.
Yes, sir, thank you so much, sir. It's my pleasure and honor to probably invite you. I never imagined in 2009, like when I have seen from the last bench of your presentation on this distance, means protection on overall, which you have talked about. Almost
Yeah, it
a
was
similar
protection. I
session.
remember in that outside Bangalore.
Yes,
Yeah.
yes, sir. Last bench, like that's what. As by the time I'm just a very beginner and I was not really able to, so I collect all the informations which you have thrown in the sessions. Only the two stories which I remember still. But I guess like the sessions probably has thrown quite a lot of informations for the audience. I guess like so say the sir has touched quite a lot of different areas, not really in depth, but like he has thrown out all this possible.
Yeah. That is the spirit also. Here, I'm not trying to teach things which you can use tomorrow in your job. I'm sorry if that was the intention. Possibly I'm wrong. I try to trigger your imagination, trigger your, as I said, the right side of your brain rather than the left side. Okay. So we are all humans, and protection is art and science. So sometimes you need to give a little bit of tweaking on the art side. And I think if I have achieved that, I'm happy. That's all I'm saying. Yeah, sure.
Yes, sir. Thank you so much, sir. It's
Thank
my
you. I
pleasure
really
and
appreciate.
honor
I
again,
really,
probably to
and
invite you
I
as a
think it's my
speaker.
pleasure. I always enjoy interacting with people, especially whatever I know. I'm very happy to share, and I think, as I said, I have been volunteering for IEEE. The basic motive is to share knowledge and make sure that as community we bring a smile on the faces of the people whom we serve. Ultimately, it's not money. It's not about anything else, and it's always pleasure to interact with people in your expert field. So it has been my pleasure too. Thanks a lot, Kumar. Thanks everyone,
Thank you.
the audience, and
Thank you.
those people who are going to watch this video later. Thank you very much. Take care.
Thank you. Thank you all. Thank you so much, sir.